Hey, chemistry. We're up to the end of our chapter with chemical reactions. We started out talking about physical changes, touched on a little bit of chemical changes, which chemical changes will always involve a chemical reaction. So let's get started. Let's start this reaction. And again, once more with the delicious grilled cheese sandwich. Kind of making me hungry just looking at it. And again, we had to apply some heat to that sandwich to make the cheese melt. In this lesson, we're going to talk about learning how to recognize whether this burning match is a chemical or a physical change. Big question, what always happens during a chemical change? When we use words such as burn, rot, rust, decompose, break down, ferment, explode, blow up, and corrode, I'm adding some here, we're usually talking about a chemical change. And by definition, that's the ability of a substance to undergo a specific chemical change, which means the substance you have is going through a reaction. Iron metal itself can combine with oxygen to form an iron oxide, which we know is rust. And that's a chemical property. We can't observe that ability. We can't observe that ability happening unless it actually happens, unless that reaction actually happens. This is not a physical property. If it were a physical property, we'd be able to see it without the change happening. But since a reaction is actually happening, we're going to consider this a chemical property because it goes through a chemical change. Again, you have iron rusting, burning wood like in a stove or a fireplace, metabolism, digesting food, cooking, which involves either frying or baking, the batteries, whether they're your calculator, your phones, or your cars, fireworks, the classic vinegar and baking soda mixture, food rotting, and electroplating. That's examples of different chemical changes. What you end up with is going to be different from what you start out with. When you take charcoal and break it into smaller pieces, well, you're not doing anything with it except breaking it into smaller pieces. You've got a physical change. What you started out with is the same as what you ended up with. Even though the charcoal pieces are not as large, when you do apply a flame to that, it's probably going to be easier to light because now your pieces have a better surface area. We'll get into that later, too, when we talk about solutions. During a physical change, like what we just saw, that composition of the matter doesn't change. But then again, that physical change just involved crushing up the carbon, or crushing up the carbon or the charcoal. With a chemical change, say we light a match, throw it on there, or ignite it, set it on fire somehow. The composition is always going to change. You're always going to get something different at the end. When that charcoal is heated and burned, the substances in the charcoal, the carbon, and the other stuff that there react with oxygen in the air to form other substances. In a lot of cases, you're going to have some carbon left behind, and you're going to lose some water vapor. It's going to look like you had less stuff when you ended up your grilling session as when you started out with just the charcoal. That's actually not quite true. What you start out with has to equal what you end up with. Let's stay right here for now. Chemical change is also known as chemical reactions. One or more substances changing into one or more new substances. And then what you start with, think about the left side of the arrow in a chemical reaction, that would be the reactant. That's the stuff that we put together to cause the reaction. It could just be one substance that's going to break down. We're going to get into types of reactions later. And what you get out of the reaction, what is produced, is known as the product. Could be more than one product, could be just one. It just depends on the reaction you're dealing with. But just something to know. The elements you start out with the reactants, you have to end up with the same products. Maybe they're shuffled around, but what you start out with, you have to end up with. Maybe in a different form. Again, carbon and oxygen are our main reactants with burning a charcoal because essentially we're burning carbon in oxygen, and what you get is carbon dioxide and some carbon ash as the main products. Now, what is always true of a chemical change is never true of a physical change. Our composition, with chemical changes, the composition of matter will always change. Let's see, what was going to happen is probably just the elements are going to be shuffled around or rearranged to make new substances. But during a physical change, we don't change the composition of matter. With filtering, with chromatography, trying to think about what we did for section 2, and distillation, we don't change what we have. We're just separating things. We're just physical changes. We're separating things that were never chemically combined in the first place. During a chemical change, we're shuffling everything around because we have to send the substances through a chemical reaction. But we have clues. It may be a mystery, but with any mystery, there's always clues. Possible clues. Notice the emphasis on the word possible. Air quotes. Possible clues to a chemical change can include a transfer of energy. Maybe something gets hot or cold. Something goes pop. You hear noise or light or something. A change in color. Not so much necessarily that something has the physical quality of having a certain color, but you see the color change. Gas being produced could be bubbles, could be an explosion, which goes along with energy, or the formation of a precipitate. I have a video of that in the Nearpod that we're going to look at. But again, I'm emphasizing these are possible clues. Every chemical change is going to involve a transfer of energy. Energy stored in natural gas, whether you're cooking on a stovetop or on a grill, you've got energy stored in that gas used to cook the food. When the methane in natural gas, let's say for instance, the methane if you're cooking on a stove and probably propane if you're on a grill, when that chemical combines with oxygen in the air, you're going to give off energy in the form of heat and light. Some of this energy is transferred to the food and absorbed by it. That's going to make changes in the food. For example, here's good old roasting marshmallows. Fall of the year, we like to have marshmallow roasts over a good campfire. Again, that energy that's transferred to the food causes chemical changes to take place. If you think back to section 2.3, this is what's happening with bread when you toast it. But if you go too far, you're going to make too many chemical changes, and you're going to cause a big pile of carbon to be formed. Of course, the food may change color and brown up as it cooks. And that's another clue that chemical changes are occurring. And sometimes, and I've seen a meme on Facebook asking about what level do we like our marshmallows toasted. Could be just really lightly, or it could be completely charcoal black on the outside and nice and gooey on the inside. But that's telling us there's some kind of change happening. And then if you happen to be the person that helps out with the house cleaning, you might have dealt with the ring of soap in the bathtub. That is a precipitate. That soap scum is a precipitate. Of course, we've heard of rain and snow as being precipitation, something falling out of the sky. Think about a precipitate as a solid that forms in a liquid mixture and then settles out. In this case, this precipitate of soap scum settles on the surface of your bathtub or your sink. That's another very good definition, hint, hint. Now, some bathroom cleaners that you can use, you spray on there, and they start to bubble when you spray them. Those bubbles are produced because what's in the cleaner is causing a chemical change, and it's producing a gas. And then again, production of a gas is one of the hints that you have chemical change happening. But, and it's a big but, if you observe a clue, if you can see bubbles happening, you really can't be 100% sure that a chemical change has taken place. It could be physical. And we know that energy is always transferred when matter changes from one state to another. When you boil water, you're sending some of that liquid water into the gas phase, and you're going to form bubbles. You open up a Pepsi or Coke, Dr. Pepper, those bubbles are going to form because what you've got in the sealed bottle or the can is carbon dioxide stored in there, and it's going to escape when you open up that drink. But those bubbles are not a sign that we have a chemical change happening. So that's why we're saying it's a possibility out of those four possibilities I listed a little bit earlier. The only way to be 100% sure that a change has occurred is to test the composition of a sample before and after the change. Oh dear, I forgot to delete that slide. Well, obviously, as you can see, we're getting into conservation of mass. A little earlier, I talked about the elements that you start out with in a reaction, you have to end up with the same elements. You have to wind up with the same masses. They can't just disappear, and you can't just make new masses. You can't just magically have carbon appear or twice as much carbon appear where it was not there before. You can't have it disappear. Big question. How are the mass of the reactants and the mass of the products of a chemical reaction related? Again, back to wood or charcoal burning. A substance in the wood combined with oxygen from the air. You wind up with carbon dioxide. And from your surroundings, that's going to escape. As the wood burns, a whole bunch of matter is going to be reduced to a small pile of ashes. And it looks like you've lost mass. Like, say you had a 5-pound log and you burned it and you get 3 pounds of ashes. And it looks like I lost matter, but you didn't. What happened is you lost some carbon dioxide to the environment. If you were able to kind of close the system and keep everything together, you'd see that the 5 pounds of carbon in the log and then the oxygen in that system, it could be equal to the ashes you get and the amount of carbon dioxide that you get at the end as products. During any chemical reaction, the mass of products is always equal to the mass of the reactants. In this case, you've got some wood burning and oxygen. You have your mass of ashes, and if you were able to capture the carbon dioxide gas and weigh it, you could add that to the mass of the ashes. I can't talk. Again, this is on Friday afternoon. I'm getting a little lispy, a little tired. You add that to the masses of ashes, and also you've got some water vapor getting sent into the atmosphere. If you could trap that, add that to the mass of the ashes, and that's supposed to equal the wood and the oxygen that you started out with. We have a special name for this. I'll get to it in just a second because all of a sudden I jump back to physical changes. I was talking about a chemical change with the burning of wood. Now we have physical changes. When you take 10 grams of ice and you melt it, you get 10 grams of liquid water. You didn't magically make more water, and none of the water disappeared. And again, our term for this is the law of conservation of mass. I will refer to it as LOCOM, as an abbreviation, LOCOM, LOCOM. Any physical change or chemical reaction, this applies to both, mass is conserved. You can't create it. You can't destroy it. You can only shuffle it around. Remember that. Again, classic example. If you were able to, excuse me again, sorry guys. If you were able to have a reaction occur, notice we have two substances, both clear-looking liquids, that have a collective mass of 43.43 grams. If you were able to quickly mix those together and seal the containers really, really, really quickly, you'll be able to see that what you started out with is going to be what you ended up with. Mass of the products should be 43.43 grams. When the liquids in the figure mixed, those two in particular react. None of the products are gases. So in this example, I kind of lucked out because you could actually mix them together and maybe not have to close the container really quickly because you don't have any gases liberated. So remember LOCOM, law of conservation of mass. You can't create mass. You can't destroy it. You can only shuffle it. And as usual, and again, if you have any questions, problems, anything coming up here, before I see you in our next class period, send an email my way. Send me an email. I'll try to help you out. Bye.